Sorry, nothing personal. He's a senior scientist at Mars for the Mars Exploration Rover project and the Geology team leader. Welcome, Dr. Rice.
Well, thank you all. Good evening, and thanks for having me back. It's always a pleasure talking to y'all. I appreciate everyone's interest in what we're doing out there. And so hopefully it'll be an interesting presentation tonight I'll give you. You ready for me to start?
We are. Yes.
Okay. Yeah. Well, this picture I have up here now is, if you look, notice it's actually moving. And you see our rover there in the foreground. It's called Perseverance. It's about the size of a Mini Cooper car, weighs about a ton. It's nuclear powered. It landed a little more than a year ago on February 18th, 2021. And if you look out there, that's our mast cam camera that's swiveling up there on the mast. That's the camera imaging system that I work on. And we're taking a picture of our helicopter, Ingenuity, sitting out there between our tracks. If you look out there. And Ingenuity weighs about 4 pounds. The widest span, the rotor span, is about 3.5, 4 feet. And this is the first time we were flown another aircraft on another planet. So it's been a fantastic mission so far. But let me get started here. Let's see, next slide. Why is it not advancing? For some reason, my slide's not going anywhere now. It's locked up. That's not good. Because it was working earlier. Okay, there we go. All right, I don't know what happened there. Anyway, we launched out of Cape Canaveral Air Force Station back on July 30th, 2020 on a Atlas V rocket. And 203 days later, we landed on Mars. I mentioned February 18th. And this is the most recent status report of our mission, because I wanted to kind of give you a summary of what we've been doing last year, and also tell you basically what's happening literally yesterday on Mars. Our report hasn't come out for today, but you can read this. I won't go through all of it, but the rover Perseverance and our helicopter Ingenuity, both are healthy, stable, working perfectly on Mars right now. We're in the process of doing a drive to the Delta front, which is the reason we landed in this crater called Jezero. And I'll show you a picture of this to give you an orientation of what this looks like. And so we're in what we call a rapid traverse program right now. The rover has driven just over 7 kilometers. We've collected 8 rock cores that will be brought back to Earth, 1 atmospheric sample, and a witness tube, which is kind of a control. It was just to see how the tubes that we have, titanium tubes, how they reacted. It's been sealed since it lifted off from Florida, and we won't use that tube. Like I said, it's like a control tube. Helicopter has completed 23 flights. The 24th flight is coming up in the next couple of days. And you can see, I mean, the helicopter was a technology demonstration mission, and it was only supposed to, at best, do 5 flights. And it's exceeded all wishes we thought we could do with that. And it's going to continue to go with us on our drive to the Delta. The mission goal is to study the geology of Jezero crater. Jezero crater is an ancient lake bed. There's a lake there probably 3.5 billion years ago, we think. We'll know when we get the samples back, and we can date this stuff. We'll know exactly how old it is. The other objective here is astrobiology, looking for signs of Martian life, because a lake is a good place to look for organisms being preserved in delta sediments, fine grained sediments. And then we're actually collecting samples that are going to come back to Earth for the first time. No mission has ever collected samples to be brought back. And all this is feeding forward into someday, not too far down the road, hopefully, that we get astronauts up there. And, really, when you really want to get the science done, astronauts are the best people to do it. I mean, these rovers and helicopters we have, they're doing great stuff. Don't get me wrong, but astronauts are just better. Human beings are better explorers. We're more adaptable, flexible. We can do stuff a lot quicker than the robotics does. Also, we can take in what we're seeing and do construct a hypothesis as we're there, collect the data, test it. Whereas a machine just does what we tell it to do. It doesn't think. It just basically carries out our orders. And here's our rover. I won't go through each instrument on here because I know you can read this. And like I said, it's about the size of a Mini Cooper. At the back of it, the aft end, under the word Mastcam Z, that's the camera I work on. The Z stands for zoom, because we can zoom in 110 times. We can also do some video with these cameras. But below the word Mastcam Z, if you go straight down, you see this kind of silver, like trash can or cylinder. That is an antenna, but off to the right of that, there's some fins there. That's our radioisotope thermoelectric generator. This is a nuclear powered rover. And then you get the arm. The arm is about 7 feet out when it's extended, with the drill out there and some instruments, Sherlock and Pixel. But that's the working end of our rover in terms of collecting samples out there on the arm. This is Jezero crater. It's about 40 kilometers in diameter. It has a ancient channel or river that flows into it off to the west and the left-hand side. And it filled up as a lake, and eventually at some point it spilled out. There's an outlet channel up there in the upper right where the water ran out, like a bathtub filling up with a lot of water. And there you can see the Jezero Delta at the mouth of the inlet valley channel. As if you're familiar with deltas like Mississippi River Delta, the Nile Delta, these are rivers flow, they pick up sediment, rock, gravel, sand, and they carry it and transport. And then when they enter a standing body of water like a lake or an ocean, the velocity of the incoming water slows down and it drops its sediment load and it forms a feature called a delta. And so there is a delta at the mouth of this channel. This was one of the prime reasons this crater was selected, the delta. And the black ellipse there was our landing ellipse. We were going to land somewhere in there, and we know exactly where we are now because we're on the ground, obviously. And we did a pretty good job. This is an oblique view from orbital images from the HiRISE camera from Mars Reconnaissance Orbiter, looking at the delta to the west, kind of looking upstream of it. You can see the delta, and this is an amazing picture here. This is on our way down during landing. We come down on a heat shield, then we have a parachute, then we fire our rockets. But while we're hanging from the parachute, this HiRISE camera I just mentioned on the Mars Reconnaissance Orbiter caught us drifting down to the surface of Mars. So it's really you can see the delta out there. It's a really amazing picture. I mean, just when you think about the timing, the millisecond split timing you had to have for this, to get this thing, it's amazing stuff, and the resolution of the camera. But after all, this stuff is rocket science, So, so now here's where we landed. This star, it's called named after Octavia Butler, who was she wrote some science fiction stories, a couple about Mars, but most weren't about Mars. But she was a science fiction author, so it was named after her. And that's where we landed. It was well within our ellipse, pretty close to the delta, off to the left of the picture here. And so that's kind of our local neighborhood right now where we've been working last year. And I didn't want to try to choke up the system, but if you get a chance, there's a landing video link down here, because I was afraid to try and run that because, sometimes things get jammed up and they freeze frame and everything. So if you get a chance, you probably saw this when we did, but it's amazing footage and it's all live. I mean, not live, it's captured live when it happened, but it's video, it's no animation. It's our actual rover coming down, landing on the surface of Mars with the retros firing, and you see the carrier stage drift away. There's cameras looking down and looking up. So if you get a chance, if you haven't seen this already, I've seen it many times. I never get tired of looking at it. It's hard to believe this is reality. It's not an animation. This is a real thing. And anyway, that's our rover being lowered down on some cables from the hovering part, which is called the sky crane, on our way down. That's an actual real rover. I mean, it's a real picture there. Once we got on the ground, this was one of the first pictures we took. You can see we landed right on our wheels because we cut the cables, and the sky crane part flew off and crashed about a kilometer away from us, like it was supposed to do. This job is finished. So you can see our tracks down there, but also if you look up there, you see that's our scour zone with our retro rockets on the way down, blew all the dust, and it's a little lighter colored than the rest of the surface. It was a very energetic event. If you watch that video, you can really see stuff going like crazy, kicking around down there, dust and stuff. And these are some of the first rocks we saw. We gave it a nickname as pavement stones. Some people call them pavers. They look like they're flat-lying rocks in the area, and it's pretty common where we are, it turned out. So this is one of the first rocks we sampled, these type of rocks, because it was pretty, you want to sample something that's pretty common. You also keep an eye out for unusual things, but you want to sample what generally is there for figuring out the geologic story. So these are the rocks. We didn't know what they were for a while. The big debate was, are they sedimentary? Are they volcanic? What are they? And because we're on the floor of an old lake. And but it turns out the story is these aren't sedimentary rocks. These are volcanic. Well, they're igneous rocks. There's a debate still on the team. Are they from lava flows or like I don't know if you're familiar with geologic terms, but sometimes you have rock magma coming up from below and cause intrusions. And at the time, they're still covered, the surface is covered over. And I don't want to get too technical and bore you, but a lava flow is when lava is flowing on the surface. Magma is when the lava is still underground. It has not breached the surface, if that makes sense. So, but these rocks were not lake beds like we thought they might be. Mars always has surprises for us, and you got to be ready for those. And that's part of the nature of the business. So we're kind of scratching our heads like, where are the lake beds? Well, to this day, we have not found them yet. So we're still looking, but we're going to the Delta, and we think the story is going to change there. But this is kind of an igneous story right now. This is another rock. This was named after a Navajo word, Maz, and that's the Navajo word for Mars. So that first rock we looked at was called Maz. Turns out, with our instruments, it has igneous mineral grains, basically pyroxene and plagioclase. It's like it's from a lava flow, so it's igneous rock, like I just told you. However, it does have some evidence of being altered with water on the surface. You know, it's been sitting there for billions of years. So water was in the area, and there are some clay minerals there, but they're not sedimentary rocks like sandstones or mudstones, you know, you expect in the bottom of a lake. Getting to the helicopter, I think everybody was excited about the helicopter. It's great stuff. I mean, picture I already showed you. Let me go to the next one. This picture right here, if you look up there, kind of like in the upper right part of the image, you see a little black dot. That's the helicopter flying right there. And that's our camera captured that. And that's the crater rim in the background. Yeah, exactly. That's Ingenuity flying. The first flight is coming up this anniversary. First flight was on April 19th last year. And I got a video here. Well, I'll show you in a second. The helicopter has cameras on it. And this is a picture it took of our rover. That's a picture taken. The cameras aren't as good as what we have on the rover, but we still have some decent cameras. This is zoomed in a good bit. But this is a picture Ingenuity took while it was flying, looking back at Perseverance, the rover. So that's a cool picture. I've never seen a rover like that, you know, taken from a distance on Mars. You hadn't had the capability to do it. So that's, you know, that's Perseverance sitting there. This is a picture taken while the flight is flying, and you can see it. The camera, you know, it's pretty good. That other picture I had to zoom in a good bit to see the rover because it's off in a distance, but pretty decent camera. And you can see a little crater there in the center of the picture. If you look off to the left, that's one of our landing legs up there. It's kind of a bluish color to it. And then you look off in the distance out there, upper part of the screen, that's looking at the Delta off to the west there. And so that's kind of a bird's eye view we get from this helicopter. And if this works, there you go. That was one of the first flights. It basically just went up and came down. But we captured it with video. We can't get video of all the flights because sometimes the rover is too far away. We can't see it. And but that was, you know, basically the first flight about a year ago. Pretty amazing stuff. And like I said, there are some other videos out there. You can watch it basically get up and fly out of the screen and come back, some of the longer flights. Like I said, this was, as of today, we've done 23 flights. Flight number 24 is going to be within, I think, probably by Monday. It's initially just a technology demonstrator, and we're now currently in operations phase, which is still working, and it's a solar powered. So a solar panel up there on the top. You see the rotor blades. This was a test we did before we flew it. And this is kind of a cool story here. Under the solar panel, there is a piece of fabric from the Wright brothers plane, which is pretty cool. And since this is the first aircraft ever flown on the planet. The picture off to the right is kind of busy. The really solid green, kind of neon green, that's the flight path that Ingenuity has done. And the green dot up there, if you can see, it says Seta. That's a Navajo word for sand. That's where Ingenuity is right now after the last flight. And the white line is what the rover has done the last year. And the blue dot up there is where we are as of today at the top. And then the green running off to the left, that's our course taking us to the Delta that we should arrive there probably the first week or so of April. So we're closing in on that. And then as we get to the Delta, we're going to collect samples there, of course. And that's where we think we're going to find the some lake deposits and flood deposits, water deposited rock, basically sedimentary rocks we should encounter there. So our mission will get kind of back where we thought we were going to go when we went here, getting into sedimentary rocks as we leave these volcanic rocks where we've been up to this point in the mission. We've got some weather instruments on here. Here's the most recent weather forecast from Jezero crater. It's actually a couple days back. We don't do it every day. We build it up and report it once a week, roughly. This most recent one, we're in the northern hemisphere of Mars. It's early autumn up there. And you can see the temperature, daytime high is 22 degrees. You know, it gets a little chilly at night, about 119 below Fahrenheit. But, you know, Mars is a pretty cold place. A lot of people think Mars is warm, I think because it's called the red planet, but it has nothing to do with temperatures. The red is from the iron oxide in the rocks. Basically, it's rusty. But so you can see the temperature. We do monitor wind directions and things. With the sensors, if that has some issues, they work some days, sometimes they don't. But our wind, we've actually recorded dust devils coming through here. And this is kind of a cool picture. Everybody was shocked to see this. This is a time lapse of all this dust. A gust of dust is blowing through the area. That's a very dusty place. And so Mars, you know, you got to think about Mars. It's a desert world, yes, but it's a cold desert. And most people, when they think of the word deserts, think of stuff like here in Arizona where it gets pretty hot. Well, desert by definition has nothing to do with temperature. It has to do with the amount of moisture that's available. So there are cold deserts on Earth, like in Antarctica, you know, the Arctic regions. These are called polar deserts. So if you want to think about Mars, it's kind of like a cold polar desert. But there are winds there that pick up this dust and stuff. You can go and listen to some sounds. You know, hear the wind blowing on Mars with our microphones that recorded this. The speed of sound on Mars is about 200 miles slower than it is on Earth, and that has to do with the density of the atmosphere and temperature of the atmosphere. So the speed of sound is, you know, even on Earth, it's not always the same thing. It depends on atmospheric pressures and densities and things. Also, the composition of the atmosphere comes into play. Mars is mostly CO2, and, you know, our atmosphere is mostly nitrogen, about 20% oxygen. But there are some recordings, you can hear it. If you have some, it's usually good to have put on a headset to hear it because it's kind of a low hum. You can hear the winds blowing. Sometimes you can hear the actuators on the instruments moving around and stuff. The Delta, which is the prime objective of our mission, we're on our way there. I'll just move on. We had our first science paper came out back in October on the Delta based on our remote sensing observations from the ground. And we've zoomed in, and what we found out on the Delta, we saw layers from orbit. We're seeing more layers from the ground. Our cameras we're better, we're closer. But we're seeing on the top, there's a lag of boulders on the top of the Delta. Some of these boulders are pretty big, you know, about 5 feet across. And that was kind of surprising. We weren't sure we're going to see that or not. We didn't know we were going to see, really, I mean, in terms of that kind of detail. But we see all these boulders, and these boulders indicate that late in the history of this Delta, there were floods that went through that river channel. And they were pretty decent sized floods. You know, be able to move a 5-foot boulder, that takes a lot of water. And our speeds, we can get that out, work it back, you know, anywhere from 4 to 20 miles an hour. The flow of water in these floods later in the history of this lake. So that's something we hope. We're going to climb on top of the Delta eventually and collect samples. And one of these boulders we would like to sample because that boulder was brought in from a distance way upstream somewhere. And that may allow us to be able to look at some rocks that normally we wouldn't be able to see. The river did all that work for us, you know, billions of years ago. So we don't have to drive all the way up there. This is a cool picture. This is one of these things. This feature is called Kodiak. This is what we call a Delta remnant. We think the Delta was a lot more extensive in the past, but it's been eroding back wasting as erosion takes place over billions of years. And this is a chunk of it laying out there kind of isolated. And early on, we thought we'd visit this, but I don't think we're going to now. I think we're going to concentrate on the main Delta. But you can see some horizontal layers in there and also some tilted or inclined layers. Those are called cross beds. And these structures that we see here are typical things you see on deltas. They're called top set, foreset beds, and bottom set beds. And we see these exact same things in delta deposits here on Earth. So, you know, this is just further indication this was indeed a delta. It's a very ancient delta. I mean, like I said, it's about 3.5 billion years old. It's been sitting there after this the lake dried up. This is another feature, and unfortunately we're not going to be able to visit this one. I was pushing on the team to visit this. It was in the opposite direction of the delta. This was further away. It's called Santa Cruz, and we're not even sure what this thing is. We think it's a delta remnant, but it looks very different because this has a flat top. Okay, this one doesn't. And that shape or morphology is telling you something about the material it's made out of. And the thinking about going here, which we're not going to do, unfortunately, these would have been the most distal, or the deposits further away when the river emptied into the lake. And that's where you find fine-grained things like silts and muds further downstream. And maybe this is made of that, but unfortunately, we're never going to know because we're not going to be able to go there. And it's one of the things about these kind of missions. You can't go everywhere you want to go. You get to pick and choose. You just can't do it all. You don't have enough time, the resources. And I don't know. I think it's too bad we're not going there, though. I guess we're never going to know those, what's going on here, the story. But what we've been doing, we just wrapped up what we call a crater floor campaign. And these are these rocks I was telling you about, these igneous rocks. These are the oldest rocks in the area. And we've collected all our samples, and these 8 rock samples have been in these rocks down here. They're slightly different, but the big story, they're mostly igneous. And depending, like I said, some of us think they're lava flows, some think they're like igneous intrusions, but it's still igneous rock. But these are older than the delta. They're before the delta formed. So when we get this rock and study it and get it back, we can date it. It can help us figure out the chronologic history of this area and when the delta came in later. And, you know, for sure, we're not sure. We know we got a delta there, but did this delta form over, well, there's a series of lakes in here, or just one big lake at one time, or did lakes come and go over, you know, billions of years? This is something we'll be able to figure out once we get to the delta, and especially once we get our samples back here on Earth and we can do the detailed analysis. Let's see, this is our crater floor campaign. What we did up there in the white where we landed, drove south, spent most of the mission working down in here. We wrapped that up, and now we're heading to the north, like I showed you. But all of our rock samples at this point have come in this area here. We also have something on this rover called AutoNav, so it allows us to drive further, faster driving. It doesn't really mean faster like, you're going 200 miles an hour, like an Indy 500 car, nothing like that. This rover drives at a pretty slow pace. Faster means we cover more territory. And just back around the time of the Super Bowl, we set a record that had lasted since March 2005 with Opportunity. The single drive record, how far you went in one single day, or a day on Mars called a sol. The record that was set that lasted a long, long time was 220 meters, about 700 feet, not very far. That was a record drive. And we broke that back in early February by about 100 meters, 99 meters. That's our new record in one single sol traverse. So, when these things are driving, they're not like, a remote control car in your driveway. And they're going, when you think about it, that's the furthest we've gone in one day is 310 meters, 319 meters. So it takes a while, but now we're making progress because the drives we're doing now are typically 250, 275 meters a day. And we're just cranking along. The mode we're in right now is driving to the delta. And so that's kind of what we're doing now. This AutoNav allows us to do that. As you can read that, the rover has some built-in artificial intelligence. So it gets these 3D maps it makes. And it basically analyzes that data as it's driving and tries to avoid, hazards like a big rock or sand dune. We had this in our drill assembly. When we lifted off, this was to keep everything clean and protected, but we wanted to get it out of the way and get rid of it. We wanted to start collecting rock samples. So what we did, we drilled into a rock and we left this sitting there in a rock. And when we came back, it fell out. It's knocked out now. We thought it'd be sitting there for a long time, but the wheel must have hit it and knocked it out. So it's laying. It's not upright anymore. We were kind of surprised when our wheel hit that. That's how close we were following our tracks back. But this was left there, and it gave us an idea about the rock properties. And this is the first place. Guyumes is the first area we did a rock in these pavement rocks that we talked about earlier. Typical rocks. We saw them all over the place. And what we do an abrasion first, and it allows us to put our instruments down there and get a firsthand view of what we think is going on in this rock. And then we do the drill core and capture that at the core and put it inside the rover for eventual return to Earth. So we do an abrasion first, then we do the core. And this was the first target we did down there. And once again, we put our scientific instruments down there, and it's a lot of iron, that'll hold on magnesium, but this is igneous minerals we're seeing here, not sedimentary. So once again, further proof these are igneous rocks, which just early on kind of surprised us, at least some of us. And you can see where we did our little coring here. It looks like a little anthill. And that's where we took the rock core out for the first rock core sample. Now, what happened, you may remember this back in early September, that rock fell apart. And when we lifted our core test tube, the core is about the size of a test tube, made of titanium. We lifted it up and then we take pictures to make sure the rock is in there. And sure enough, there was no rock in there. We were like, what happened to it? Did it fall out? Well, what happened is that rock got pulverized. Very weak rock interacted with water over time. And the rock just fell apart during the drilling process. The mechanics, it's a rotary percussive drill. It just beat it up and there was loose grains and it fell out. And so we didn't get a sample. That's where our atmospheric sample, that one atmospheric sample comes from, because we sealed it at the time and we didn't know until we could wait. We can get the mass of these things in there. We weigh them. There's nothing in there. We're like, what happened? And then we took a picture of it and there's nothing in there. So, we told the atmosphere people, here's your atmosphere sample. So we hope you enjoy it, basically. But we were totally surprised. And a lot of people were like, man, if all these rocks act like this, we're not going to get any samples. Well, this was the only one that did that. And we caused a lot of head scratching early on, but we figured it out. And it's just this rock was heavily eroded and it just fell apart, And we went to other rocks. We never had any more issues since then. But this is a rock, the first sample we actually collected, called Rochette, and did an abrasion first. It looks similar. And this one, we found some salt crystals in there. And so what we're seeing here, the story here, these are igneous rocks, maybe a lava flow, been sitting there a long time. Then water kind of came in, interacted with them and deposited the salt minerals. And so there is a water story here, that these rocks were altered by water after they were first formed, And you can see an abrasion hole, and then above that, the drill. You can see all the sediment that came out from our drill operation and covered up the abrasion hole. But once again, we found salts here. This is water that percolated through this igneous rock. And when we get the sample back there, some of these little salt crystals may have inclusions or bubbles in there, which would be very interesting because we'll be able to sample if there's any water that's trapped in there, at least what was left behind in that. So, this type of analysis is done typically on, ancient samples on Earth. But once we get these back from Mars and get them on Earth, we can do all this great stuff. And that's a picture of our core in there. You're looking straight down the tube. That's the rock sitting in there. It's about, I think the core was about 6 centimeters long and probably about a half centimeter wide, I think. And we're going to collect 38 of these eventually, and they'll be brought back to Earth. And just this week, they were originally supposed to come back in 2031, but now it's got bumped to 2033. So I'm going to wait a little longer for that. This is just a sequence of images showing that right there, we sealed it. We collect it. You see the core, and there's a camera called Cache Cam that's focusing on that, and then it gets sealed, airtight, locked up, and that's the size of the core tube over there. That's pretty much the size of kind of a test tube, chemistry test tube, but it's made of titanium. And so our rock cores will be stored in there. Right now, they're currently in the belly of the rover where we store them. But we're going to drop them off in a cache, 2 separate caches. Then another rover that will come, called the Fetch rover, come pick these up, bring them back to a lander with a rocket on it, transfer them in there, and that rocket will take off from Mars with a container about the size of a basketball with all our 38 samples. And then it'll be launched. There will be an orbiter up there, a rendezvous with that and capture it. And then that will be brought it back to Earth. And it will land in the desert in Utah. Here's where we are. The 8 cores, you can see the abrasion pits or holes are on here. And also the cores, the 8 cores we've got so far, and then the locations where they came from in our crater floor campaign, primarily to the south of where we landed. So then we got 8 at this point. We're going to collect about 30 more for the mission. And so we're, getting there slowly but surely. This is a picture from orbit. That's our rover sitting down there, a little white dot. That's from the high-rise camera that I've talked about several times before. If you look very carefully, you can see some of our tracks down there, especially to the lower left, where we drove around doing our investigations. And there's a rover sitting there, and that's the size of a Mini Cooper, taken from about 200 miles high in orbit around Mars. This is the summary of where we're going, what we've done. We're going to the Three Forks area. And when we get there, we got to make a decision of which way we're going to go up onto the Delta. There's a couple routes we have right now. We haven't decided on the final one, but we won't be able to really decide that till we get into that area and start taking high resolution pictures of our cameras to figure out what is the most interesting area to take, and also which is the one we can actually drive through, because some areas have sand dunes and you don't want to go through that. It's a hazard. So we got to make sure when we get down there, balance science with, what we call trafficability. Is it safe to drive the rover through there? So that's kind of where we're going to be going, that direction. And then, like I said, there's a couple routes we're looking at to get up on the Delta. This is one example right here. We'll get up on top of the Delta. And eventually, if we do this, we'll go upstream of the river that fed this thing, Neretva Vallis. I hope we do that, but there's other people who want to go different ways. So, it's one of the things, you got a team of people, everybody, we get a bunch of scientists in a room. There's a joke goes around, if you get two geologists in the same room, you'll get 3 different opinions. There's a lot of, going to be a lot of horse trading and dickering to do, figure out exactly which route we take, and it'll be a work in progress. That's kind of part of the fun of doing these things, working on a mission, being able to get in there and actively promote certain areas to go investigate, and this mission collect samples, actually. This was a picture taken about 3 or 4 days ago. Looking back to the west, you see our tracks. You see how we kind of swerve a little bit. That's the AutoNav, avoiding little rocks and things. And that's a great picture of the radioisotope thermoelectric generator there. Those little white fins you can see off to the left. And our hexagonal thing is another one of our antennas. And it's a cool view in the late afternoon. The sun's setting on Mars. And I want to leave time for questions. This is my last slide, but this just happened about a week ago. I mentioned this is the Artemis 1 mission that's out on the launch pad in Kennedy Space Center right now. And it's going to sometime, but they haven't set the exact date, maybe April 3rd, 4th, first week of April probably. They're going to do what they call a wet dress rehearsal. And they're going to fill that big giant orange tank called the core stage up with propellant of liquid oxygen, liquid hydrogen, fill it up, go through a simulated countdown demonstration test. And they're not going to fire the engines or anything. They're going to stop it around T-9 seconds. And then they'll drain the fuel out. And if everything goes smoothly, they'll roll it back to the vehicle assembly building, the giant building about 525 feet tall down there. If you've ever been to the Cape, you've seen it. It's like a giant sugar cube sitting out there. They'll roll it back in there. They'll make any final adjustments. They'll also put on the explosive devices in case it goes off course to blow it up. And then they'll roll it back to the launch pad, and they're going to launch it. And the first mission, Artemis 1, will not have any crew members. It's going to just it's going to fly out past the moon and back and just prove that everything's working, the system, the launch vehicle, and the reentry of the capsule coming back and everything. And then the launch is looking like maybe it could be May, probably June is more realistic. It will depend on what happens with the wet dress rehearsal. So anyway, this rocket is getting ready to fly in the next couple months, which it's been way overdue, over budget, but it's finally going to fly. It's called the SLS, the Space Launch System. The first mission is Artemis 1. It will fly, it'll fly this summer, put it that way, okay? It could be, who knows what they're going to find. I think this is the first time it's ever been done, so issues crop up. But I feel pretty confident it's going to fly in the next several months. And then Artemis 2 will have 4-member crew of astronauts. It will not land. It will basically do an Apollo 8 type mission, sort of. Just go and orbit the moon, prove out the life support systems and everything, communications, guidance, navigation. And that mission right now, it looks like it might be about 2 years after this one. And then Artemis 3 is the next time we'll land on the moon. And it'll be the first time in over 50 years. The last time we did that 50th anniversary is coming up this December, back in December 1972. So we're slowly but surely working our way back to getting on the moon. And the moon is kind of the stepping stone to Mars. You talk to different scientists, but I'm in the opinion that we have to go back to the moon and do this first before sending people to Mars. Got to learn how to do this. Got to learn how to live on another planetary surface. The moon is convenient. It's only 3 days away. If something goes wrong, you can get back. So anyway, Artemis is kind of the big, in terms of human spaceflight, the big deal now. And the plans after we do our work on the moon is eventually going to Mars, but that's still, to me, is probably 15, 20 years away. And I know Elon Musk is trying to do it sooner. More power to him. Hope we can do it. But it's going to be a tough thing. We're struggling to get back to the moon. And the funny thing about it is, when the Apollo program wrapped up, a lot of the guys that were in charge of running that, they were just kicking back one afternoon down in Galveston, Texas, walking on the beach, and they said, when people try and do this again, they're going to realize how hard it really was the first time around. And I think we're realizing that, it's not a simple thing to do. And when we did it the first time around for Apollo, part of the race to the moon against the Soviets, it was part of the Cold War, and the budgets were there, the money was there. NASA's budget ever since those days has only been a small fraction of what it was during the mid 60s. And it just takes longer to do these things. I think it's very important that we get back to the moon, and that landing on Artemis 3 will take place at the south pole of the moon, because that's where the resources are, namely water ice and these permanently shadowed craters. And that is very valuable for in situ resource utilization, fancy word, sometimes called ISRU. Basically what that means, if you get that water ice out of there, you can make rocket fuel, break it apart, hydrogen and oxygen. That's what's going to be in that orange tank right there. You can also, when you break it apart, if you had a chemistry class, you did this in a test tube once upon a time. You got oxygen separates out, you got oxygen to breathe. Well, of course, you got water to drink. So water ice is the most valuable resource in space exploration, So anyway, the moon's going to be a lot of stuff going on, interesting stuff there. Mars, we're doing a lot of cool stuff. We're going to get these samples back. And I think I'm going to wrap up there because I wanted to leave time for questions and answers, because I think that's probably the most important thing of these talks, because you don't want just a talking head running off his mouth. So I want to try to answer some questions if you have them out there.
We do. There's a couple of questions. First is, how does Ingenuity navigate? We get GPS here. We know where we're going. There's no GPS there. How in the world does it fly out, take pictures? How does it do that?
Well, you get it right. It's the pictures. I mean, we have pictures from orbit, so we know the general overall lay of the land, but you need better detail. And so Ingenuity has what we call navigation cameras on it. They're monochrome, black and white. The pictures I showed, there's a color camera on there. That's called the RTE, Return to Earth camera. But it uses all these images, and it has inertial guidance system on there. And the critical thing about it is those rotors, when they're RPMs, they're going around 2,400 RPMs a minute. And the Martian atmosphere is very, very thin. See, a lot of people, we tested this thing out in kind of vacuum chambers on Earth, and it flew, but you never know on Mars. And Mars, you have these winds and things. And so, we didn't know 100% it was ever going to work on Mars. I mean, we did the best we could do on the ground, and we felt confident, but you never know till you do it, And so it's a very high RPM speed. And right now, since we landed in the summertime on Mars, okay? Now we're going to the fall. The atmosphere on Mars changes. Now, the atmosphere is very thin on Mars. The atmospheric pressure on Earth at sea level is about 1,000 millibars. Well, the atmospheric pressure on Mars is 10 millibars, okay? Almost nothing there. So that's why you have those high rotor speeds, because there's not much atmosphere for the rotors to kind of bite into. And then when you fly up there, it's got a little computer in there and the body of it, and we're taking a lot of photos, and it can, it has like gyros to keep it, balanced, because you don't want it tipping over and flying, into rocks and weird stuff like that. So early on, the first flight, like I showed, the first thing we did was just had the rotor blades turn around, and then we did that flight. Basically, it went up, I think it was like 6 feet, and came back down, just to kind of get a feel for what it feels like to operate. Then with the next flight, we did it incrementally. The next flight, we went up, we went off to the right, and then back to the left, then came back down. Just want to make sure we understood how to, the controls, how they work, because we never did it in Martian conditions. Did the best we could do on Earth, but and we can only fly certain times of the day. What we don't want to do, we fly usually in the morning, because in the afternoon, the atmosphere warms up, and you get these dust devils on Mars, like that gust of dust I showed you. You don't want the helicopter anywhere near that, okay? So we usually fly in the morning, because in the morning it's less turbulence, and the temperatures aren't heating up, so you don't have these eddies and vortices in the atmosphere. And but we did notice when the seasons change, we had to change the RPMs of the rotors, had to go faster in the summertime, because the air got thinner. Hot air expands, hot relative speaking, okay, on Mars. But So yeah, it's a complicated thing, but the guys who are doing the engineers who are flying, they've learned so much now. And as we get to the Delta, because the helicopter is going to continue to the Delta, it's probably going to scout out areas to help us figure out what's the safe areas to drive in. And that Delta is about 130 feet high. Well, the helicopter so far, the highest it's flown is about 30 feet. So it's going to have to fly higher. So we're going to do some tests when we get out there. But that's going to be a great, resource to have. And eventually, that's what we want this thing to do in the future, to have like these helicopters to help pave the way and scout out and do the recon for rovers, or even when you get astronauts there, they can go ahead of the astronauts and figure out the terrain in terms of the safety of it, but also to look out for interesting, geologic areas to sample and investigate. So yeah, it's a complicated thing. It involves a lot of pictures. And even with the rover, when we navigate, it takes a lot of pictures. I mean, that's why we have a lot of cameras. We have the Mastcam Z, which takes all these great color pictures and video and stuff I show in stereo. But we also have navigation cameras and hazard avoidance cameras that look to the fore and after the rover, because those are literally our eyeballs, and we have to know where we're going. And, in football, there's a saying that you don't outkick your coverage. Well, when driving rovers, you don't outdrive your photos, because you kind of don't know what's over there. Now, sure, we have orbital photos. We can see, in terms of hazards at rover scale, like small rocks or sand dunes or small craters that don't show up in these high resolution orbital photos. You want to have it pictures from the ground. So, that's another reason right now we don't, these drives are, several hundred meters, but you still want to know as you take those pictures what's coming up. And because the last thing you want to do is get the rover in trouble, because nobody can go up there and fix it.
Yes, true. One other question I had: when you take a rock sample, are you heating the sample for outgassing and then analyzing that, or not touching it at all and just waiting for it to come back to Earth?
Yeah, you're right. We're not touching it at all. Once we collect it, we don't do anything. It's sealed, and that's what that cap, that one little video I was showing you, that little gold cap gets put on there. It's sealed, tight. Nothing can get in there or get out. And so the only analysis we do on the rock is those abrasion, pits or scours I showed you. We put our instruments down in there, and then we actually do the drill core sample near the area. So the rock won't change that much, but those samples, like you said, we don't touch them at all. Once they're collected, that's it. They're sealed in the tubes, and until they get back here on Earth and opened up, they're like they were the day they were collected.
Yeah. Wow. And you're saying the earliest return opportunity is 2033?
Yeah, I mean, it's just this week, NASA headquarters at a presentation earlier, up until this week, it was 2031. That's still a long time away, but and what they're going to do now is we were going to land the Fetch rover and on a lander, and that lander also had the rocket to take the samples off from Mars. That was all on one lander. Now they broke those up into two separate landers, and reasoning, I don't know. Safety for one, but both these things got to work. If you don't have the Fetch rover, you're not getting the samples. And if the lander with the rocket to take off from Mars didn't work, you're not getting them off the ground. So, but one of the reasons was for that is cost. You split it up, extra time. You distribute the cost over a longer period of time. It breaks it down smaller. You're still paying the bottom line price tag at the end, though. But I guess it's a sticker shock. But primarily, the main reason I saw was engineering to make the payload fairing, to put that big vehicle in there. But it was kind of pushing, stressing the system. They wanted to put a smaller, payload diameter in there, so they broke it down to two vehicles. But that's going to knock it out 2 more years, which is, I don't know. I guess when you think about that, it didn't really matter when you're talking about a decade, but still, 2031 was better than 2033.
Yes, I'll put that in my calendar.
Well, originally the 2031 date, I don't know what this now, because a lot of the details haven't been announced to us. We just saw the basic, mission architecture, how it's changing. But originally, we were supposed to get this rock samples back in September of 2031. It was going to land out in the desert in Utah, in the Dugway Proving Grounds. That will still land there, actually, and but I don't know what month it's going to be right now. It was kind of neat to think about September 2031. Going to put the countdown out there, but a little longer to wait now.
Okay.
If they keep pushing it out, though, we're going to have astronauts up there, so we better hurry up.
Elon will bring it back.
Is there a sharp temperature gradient between the ground and a few feet up on it?
Mars?
Mars, yes.
Yeah, it changes pretty dramatically because down there where the rock and soil is darker colors, it's going to absorb more, sunlight and be a little warmer down there. And as you go up, like you're saying, into the air column above the ground, temperature changes dramatically. And so we have a mast up there with these sensors, temperature and wind, and they're mounted above the ground up there because down to ground level, that even though I'm not a weather person, but on Earth, they have these things above the ground. They don't have them sitting down on airports. Usually they don't have them sitting down there on the tarmac. They have them on little towers and stuff.
Mhm.
But the great, I don't know what it is. I mean, the temperature, it changes. I know, over a period of about, I don't know, say 4, 5, 6 feet, it would change. I don't know what that number would be precisely per foot or anything,
Mm. Was there an alternative site if something should go wrong, and you had that circle in the crater that you're in now? Was there an alternative site and a whole program involved in that alternative site?
Well, that landing ellipse is pretty big. I mean, we knew with precision of our landing system, we could get down to an area about 6 miles across. And we didn't know exactly where we'd land in there because, you come down for parachute because Mars has winds.
Yeah.
Who knows what the winds are doing that day? And those winds could blow you a little bit off course. And so we didn't know. We were confident with our system because it had worked before with Curiosity rover. It's the same system. It had been upgraded, of course, some things, but we knew it was very precise. And the landing ellipse, we were certain we would land somewhere in there. We didn't know where. It would depend on, what the Martian atmosphere was like the day. Like when we entered the atmosphere, in that season, was the atmosphere a little denser than normal? It would have affected our heat shield, maybe having to stay on the heat shield a little longer. And when you go on parachutes, you just depend on local winds, and no one who knows what those are going to do because we don't have weather stations up there before we land. And but if you watch the video of the landing, you can see we're coming down, and you can see the heat shield drop off and goes down below us, and it's really amazing stuff. But you can see as we're coming down the rockets, and the rockets are looking out. There's a thing called terrain relative navigation system we had. So we're taking pictures on the way down to compare it, what we had from orbit, what we should look like to know where we are. And then you'd fire to correct it. And you can see a big correction maneuver fired in there to avoid a hazard. So if you watch that, it's almost like Neil Armstrong was in there flying a thing. You can see it take off to one side. You watch the video, it's pretty cool. And I think that one of the videos is like 3 or 4 minutes long. I think there's an annotation in there to kind of tells you what's going on step by step. And so if you watch that, you can see all this stuff going on. And because it was taking us into this area where all the sand dunes were at SATA feature, but the navigation system realized that it's kind of a hazard. You want to land somewhere smooth and flat, so it avoided that. And you can see it move, take us off to a smoother area.
Once Curiosity, you're talking about landing. Once Curiosity made it to the ground, everyone said, wow, there were so many things going, which you indicate, so many things. I did see the video of that launch. And then I was surprised to find out that you had such confidence in all of those things that something could have gone wrong, to do it again.
I mean, what you do is you test this stuff over and over and over. If you spend years, that's why it takes years to fly these things, because you build them and test them, and you test them, you try to break them. You want to stress them and see what they really can do and can't do. I mean, these, like for instance, like the actuators on a camera to make the camera swivel and stuff. We test those things on the ground in Martian, in a thermal vac temperatures and a vacuum, kind of like similar to Martian atmosphere, Martian temperature wise and pressures. But we stress these things way more than they'll ever be done, and tens of these motions are tens of millions of motions over the lifetime of the mission. We do it way beyond that, and we stress these parts come out in batches, so they're all pretty a lot of detailed notation on everything is done. You'll test this stuff. You'll try and test it years and years before you fly to see when's it going to break, and that this kind of mentality, the way you do stuff, it builds the confidence. But you never know what's going to happen because so many things can go wrong. And the thing I tell people, this kind of work is great stuff, but it's not for the faint of heart, because I worked on a mission. I worked on Mars Polar Lander. It was supposed to land near the South Pole of Mars back in December of 1999. It crashed. Okay. I spent 2 years of my life working on the cameras, testing them in thermal vac, learning how to operate our cameras, with all the mission training, the simulations went through 2 years, and we crashed and didn't get anything out of that, and when it crashes, the scientists, you lose your job. Engineers kind of move on to the next project. The scientists kind of left twisting in the wind because you have no data to analyze. Mm-hmm. And it was a low point. I'm not gonna lie, because you're out of a job, basically not because you did anything wrong. It's just Mars is a hard place to go. Half the missions fail there. And but I knew that was part of the business. This is risky stuff. I mean, the thing could blow up on the launch pad. You'll never even go anywhere, So it's just a thing you deal with. You learn to compartmentalize. It's always hovering. When I worked on Spirit and Opportunity, those missions, Opportunity went 15 years. It was supposed to go 90 days. And that was unbelievable. And you just never know. And you're doing the work. That's why we take every day as a blessing. We try to do everything we can do in that day, because tomorrow is not guaranteed. It may never come. And so we try to do the best we can each day. And that's just the mentality you get into when you work on these things, because tomorrow it's not a given, And so it's just, I don't know, a way of work. You just get used to it. I know with Perseverance, before we landed, we had a lot of new people. This was their first Mars mission to work on. And a lot of them, they were very freaked out and worried. They were stressing because of all the pressure. And, I remember when I worked on Spirit and Opportunity, that it's, you spend years training, you know what to do, but, some of it's out of your hands when it's actual automated stuff, the landing sequence and stuff, and you hope it works. And it's, that's why you really celebrate when you get down there on the ground, because that's a hard place to get. And in one piece, that is. But it's a tough business. But man, when it works, man, it's great. And the other thing about it, the more you work on it, the more you know it can go wrong. It's a miracle it ever works.
Is there a Curiosity? Is there just sort of a separate group working on collecting data from Curiosity? Is sort of an ongoing thing?
Yeah, there's a separate flight team, but there are a couple people on Perseverance who do work Curiosity. I don't know the numbers on that, but I know there are some. But there are a lot of people just strictly devoted to that mission. But there are some people that switch back and forth. Some scientists I know.
I see. Any other questions?
I got. Hi, Dr. Rice. Keith Marley. Good to talk to you again. Thank you so much for talking to us again. It's been a couple of years. I was just wondering, there's got to be people there that are expecting to find evidence of water. I'm just curious where your money's at.
Well, I mean, I was surprised. I was one of the people surprised. I thought those rocks we landed on were going to be lake beds, and they're not, like I said earlier. And that surprised me. I'm kind of like, look, we're on the floor of an ancient crater lake. Where are the lake beds? But we got fooled in Gusev Crater with Spirit, because we thought that some people thought that was a lake bed. I was one of the people who wasn't sure about Gusev Crater. But what happens, it looks like in Gusev, is lava flows came later. I mean, when you talk about 3.5 billion years, it's a lot of history there. A lot of things have happened geologically. And so the lake beds could be buried into these lava flows, if that's what they are. The other thing, which I find harder to believe, is maybe they are all eroded away and below the lake bed with these lava flows. But you think you'd find residual outliers or pockets of these rocks, and we haven't seen that. We've been looking. I was one of the ones looking for this stuff, and I was kind of finally brought kicking and screaming to agree these things are igneous rocks. I was one of the people for a while. I was like, no, sedimentary, but once we collected more and more data, you just couldn't ignore the fact. And so there's a couple possibilities. The lake beds are buried under us. We looked around some craters. We thought the crater would dredge this stuff up. We didn't see that. But the delta, I tell you, that delta better be sedimentary rock. If it's not, it's going to be. I laugh because part of this is why you do it. That's why you explore and discover. You don't know what you're going to find out. That's why you do these things. But I feel pretty confident that delta, you got that river coming in there, dried up river, Neretva Vallis. Now, the thing about that, lava could have flowed down that channel at one point, and but when you look at those fine scale layering, like I showed you, in the delta and the remnant like Kodiak, those inclined beds, the four-set beds we call them, that's what you see in sedimentary rocks, delta formations here on Earth. I mean, ancient formations like that, and it's, you know, I guess we won't know till we get there, but well, I'll be shocked if those aren't sedimentary rocks like sandstones, you know, mudstones, siltstones, that kind of stuff. And up at the top where those boulders are, might be conglomerate rocks up there and things like that. But you know, although we had a presentation this past week, a science presentation, and one of the people said, "Well, we think these are sedimentary." Somebody said, "What do you mean?" He's like, "Well, we don't know." So in the back of our minds, because we already kind of like were surprised once, you know, with the crater floor rocks, and so now I feel pretty confident because look, you have a channel that emptied into a hole in the ground. There was water in there. The questions are, how deep was the lake? How long did the lake last? The lifetime or duration of the lake? And how many lakes were in there? We don't know that. But I think we'll learn that when we get to the deltas, and definitely when we get those samples back here, because when you collect these samples, what you're doing is like reading pages of a history book with your rock samples, and also the data we're collecting on the rover for our pictures, building up the geologic story with layers and things. And but I don't know. I mean, I wouldn't, you know, you don't never know till you do it. But I think when we get there, it's going to be a different mission. It's going to be the sedimentary story that we went there to find. I think it'll be sitting there. But I guess if I'm wrong, I'll come back and eat my words. You know, I'll give you a talk in the future about that. You know.
Now, will you know confidently in, let's say, a few weeks or a few months when you get to the delta that you have sedimentary rocks, or do we all have to wait till 2030?
I think we'll know, you know, right now, if our drives keep executing right and stay on target, we should get there in, you know, early part of April. And but then we got to figure out which route we're going to take, you know, so that's going to take some time, and it'd be kind of a little slower progress there. You know, right now we're driving these, you know, 200-meter drives a day, 200 or 300-meter drives a day. But once we get there, we're going to slow down and, you know, start studying stuff in detail, because we'll be Delta. And, you know, our first sample, I don't know when that will happen, because it depends on a good outcrop and everything. And it looks like it's, you know, a representative sample and an important one. I would say months for sure, you know, maybe weeks, but I think months is probably an easy, we'll know something in months for sure, I think, with these rocks. You know, it could be, yeah, months is a conservative thing. It could be, you know, a month or two, but I think, you know, it's a couple more weeks till we get there, and then we're going to slowly kind of creep into it. I think we'll have the pictures, we'll see things, but in terms of, you know, doing the abrasion and putting our instruments in this little abraded pit to, you know, get into the innards of the rock, so to speak. That first time we do that, we haven't, you know, we don't know what kind of rocks we see, because they have to be certain kind of geometry to get our drill in there to get to it. Don't want a lot of dust on it and stuff like that. But I don't know. I'm hoping that, I would say within the first, once we arrive at the Delta, I would say in the first month and a half, we'll probably know, we'll probably abrade one of these rocks and know what's going on there.
I know he has a time constraint tonight, so we have to respect
Okay,
that.
yes.
Dr. Rice, I know you have a time constraint this evening, and I want to respect your time.
Well, thank y'all. I appreciate talking to y'all. And you know, keep me in mind. We can do it again sometime. I can give you the progress once we get to the Delta.
We do want to do this again. Let's make it number 4.
Yeah.
Right.
Okay, sounds good to me.
This is great. Thank you so
Yeah,
much.
thank you very much. We really appreciate it. Thank you.
Well,
so much.
thank y'all. I mean, I appreciate y'all's interest and your questions and stuff. And over the years, I've been doing this, and consider your friends. And so, you know, keep me in mind, and we can do this again sometime down the road, you know.
Good
Wonderful.
luck.
Very good.
I hope you
Thank you.
find the pot of gold at the end.
Yeah, we do too. I think we will. I think we will. So stay tuned, you know, it'll be in the news. All right, goodbye.
All right. Good
Bye
night.
now.
Thank you very much, Dr. Rice.
Have a nice night. Bye-bye.
You
Good
too.
night.
Be well. Good night.
Bye.
Then I'll leave it to, there he goes. Ah, that worked out nice.
That worked out great.
Okay, I'm going to end the live stream.
Yes, thanks.